recording has started. So thank you all for attending this Applied PDE seminar at the University of Washington. This is our first seminar of this spring quarter. So maybe it makes sense to go over the logistics a little bit. So we'll actually have, I believe, 9 talks this quarter. These talks will, with speaker consent, be placed on our YouTube channel, which is why they are recorded. If you have questions during the talk, unless the speaker says otherwise, feel free to put them in the chat or just interrupt. And then if you put them in the chat, then we can relay them to the speaker. And of course, we'll also have time for questions after the talk, which will not be recorded. So with all that said, it's my pleasure to introduce Ahmad Abassi today. Ahmad is a PhD student at the University of California at Berkeley, advised by John Wilkening. And today he's going to tell us about the semi-analytic theory and computation of finite-depth standing water wave. Thank you, Ahmad.
Thank you, Professor. Can I start?
Yep.
Yes, please do.
Okay. Thank you so much for the introduction, Professor, and thank you to everyone for coming. This represents joint work with my PhD advisor, Professor John Wilkening, and today we're going to talk about the semi-analytic theory of finite-depth standing water waves. So I thought it'd be nice to begin with an illustration, a video illustration, actually, of a deep water standing wave. This is courtesy of Professor Wilkening. And this is a shallow water standing wave, where we see that the crest is higher because it's closer to the bottom boundary against which it can kick. So this is nice. And our goals for today are to first and foremost to construct a semi-analytic theory for standing water waves in domains of finite depth, to generalize the groundbreaking infinite depth semi-analytic theory developed by Schwartz and Whitney and later vindicated by Amick and Toland. We also wish to demonstrate the existence and uniqueness of a solution in the space of trigonometric polynomial through the exhibition of a recursive polynomial. And finally, we wish to perform numerical simulations to gain insight into the analytical properties of our semi-analytic expansions. So by implementing our serial algorithm in parallel on a supercomputer. So we take the following approach. We begin by augmenting the complex analytic techniques and ansatz used in the infinite depth setting to an appropriate finite depth setting generalization. We derive the ODEs of the problem governing the Stokes coefficients that are dictated by the physics and the geometry of the standing wave problem in finite depth. We then propose our iterative algorithm to solve the system iteratively and recursively, and through the algorithm we exhibit existence and uniqueness of the solution in the space of trig polynomials of a specific form through an inductive argument that follows our algorithm, and we conclude with our numerical simulations on a computer. So as far as the problem setting and the governing equations, what we study today, the objects we study are, as we said, standing waves on an inviscid, irrotational, incompressible, two-dimensional fluid domain of finite depth. And as usual, we identify the real plane with the complex plane, and we parameterize the free surface and the velocity potential in the standard way with the standard notation. And the two equations governing the problem are the two differential equations that govern the free surface, which are the dynamic free surface condition and the Bernoulli equation, or Bernoulli free surface equation. And these basically dictate and govern the time evolution of the free surface. They're given right here. And in addition to this, we assume that the standing wave and fluid velocity are spatially periodic with a period L in physical space. And we'll get to the physical space part versus conformal space in a moment. And here's an important observation, actually, that the governing equations of the free surface can be viewed as only involving the surface variables by observing this identity right here, and also that the normal derivative of phi can actually be computed by var phi by applying the Dirichlet-Neumann operator, which is, I believe, quite standard. Here is an illustration of our conformal map to pull back the physical domain of the fluid domain into conformal space, the W plane on the left being conformal space and the Z plane on the right being physical space, the one in which the fluid actually behaves. And as we can see, this dashed line right here on the right, and the physical space represents a mean free surface height of 0 in physical space, which turns out to be a physically relevant constraint that we've decided on in order to actually dictate a unique solution to our problem. So the conformal map we use basically, as we said, pulls back the fluid domain to the complex half plane. And a key observation and difference from the infinite depth problem is that the pre-image of the conformal map, unlike the infinite depth problem where it was the bottom half complex plane, is now a strip that evolves in time where the bottom boundary is actually a height function. So the bottom boundary, instead of being beta equals minus infinity in conformal space, is now beta equals minus h of t, where h is a function of time that dictates the height in conformal space. And as usual, beta equals 0 in conformal space is mapped to the free surface of the fluid in physical space. And then we, of course, set the period of the conformal domain to be 2 pi, as shown on the previous slide, so that the bottom boundary evolves in time, and we don't need to worry about anything else besides time for the bottom boundary. And here is just something standard where we denote the conjugate harmonic function to phi in physical space by psi, which is the stream function, and we define the complex velocity potential in conformal space using big phi in the standard way, where W is the conformal space variable and T is just time. And X and Y represent the real and imaginary part of Z in physical space. So the Cauchy-Riemann equations of the problem state this sort of inner dot product with the normal, where S derivative alpha is just the arc length element of the parametrization of the free surface, and then the kinematic and Bernoulli free surface equations are easily translated to conformal variables instead of the real variables. And these are the ones that we actually want to solve because we solve our problem using conformal space instead of physical space, just because it makes a lot more sense and it's more tractable, obviously. And what we're searching for are standing waves, which are the symmetric time periodic solutions of the above equations. These two right here in terms of conformal variables. And now it's time to non-dimensionalize before embarking on our journey to actually solve the equations that dictate the problem. We non-dimensionalize the conformal map as follows. And then we sort of normalize the velocity potential like this. And this S frequency dimension, this is just a dimensionless frequency number that's related to the Freud number. And these are the same non-dimensionalizations used by Amick and Toland and Schwartz and Whitney in the infinite depth problem. And much like they did, we define an auxiliary non-dimensionalized big W function that's the ratio of the conformal spatial derivatives of f to z. And the complex conjugate of this dimensionless, this is a dimensionless velocity that's actually pulled back from physical space to conformal space, where it's indicated at the bottom of the slide. And these are the three main non-dimensionalized PDEs of the problem, which dictate the free surface and the geometry of the problem. The first one is called the auxiliary equation. That's just the definition of the W. And this one is expected to hold throughout conformal space. So beta goes from minus h of t to 0. And the last two are the kinematic and Bernoulli free surface equations, respectively, non-dimensionalized and stated in terms of the conformal variables. These only apply to beta equals 0, the free surface in conformal space. And the key to solving our problem in the semi-analytic framework begins by proposing an appropriate ansatz for the Fourier representation of our three main dimensionless functions, or quantities, if you will, for their Fourier representation. And we want to do two things. We want to propose a sensible ansatz in the numeric sense, and we also want to propose an ansatz that generalizes Amick and Toland and Schwartz and Whitney's infinite depth ansatz in such a way that it generalizes it. But as we will see, we won't be able to recover the infinite depth solution by from the finite depth solution by simply taking the depth to be the dimensionless depth parameter to go to infinity in the formal limit. So this is the Fourier representation of big C. This is the Fourier representation of big W, and this is of F, where the first two are sine series and the last one is a cosine series. And h, as we've explained, is the height function dictating the time evolution at the bottom boundary of the conformal image of the problem. And mu0 turns out to be a dimensionless fluid depth, actually, because as we saw on the slide representing the conformal map, as we will see, this represents the depth in physical space with dimensions. And if we just look at our ansatz at the bottom boundary, what we see is at the bottom boundary, the imaginary portion of this is minus mu0, and the imaginary parts of these on the bottom boundary will be 0. This indicates that mu0 is indeed the dimensionless fluid depth in physical space, and that the vertical component of the velocity on the bottom boundary is 0, and the stream function is constant and actually 0, indicating that there is no fluid flux crossing the bottom boundary, which is logical and what we want. And it turns out we can recover the form of the Schwartz and Whitney and Amick Toland ansatz, where they propose something that looks quite similar to ours, only theirs were in this more standard complex Fourier series representation where the coefficients are temporal functions. And if we just take the limit mu0 to be infinity, we have this corresponds on the bottom of the slide. And as we will see, a main difference from them, besides the fact that we use sines and cosines, is these normalization factors of Cauchy's of p times mu0, which are necessary to actually recover their ansatz. Just to take mu0 goes to infinity, so it's a normalization term, if you will. And this is our ansatz for the Stokes expansions of the temporal coefficients of the Fourier representations of our ansatz, where A, B, and C and S have expansions in epsilon, where epsilon is the wave crest or amplitude. And A, B, C, and S have the same proposed Stokes expansions as in the infinite depth problem. The only thing we now need to add or slightly modify is the height function, which we will propose a Stokes expansion for in powers of epsilon. And this is what we propose for it. As in the infinite depth problem, the amplitude is defined as half the vertical crest to trough height. So half the vertical component of the imaginary component of big Z at 0 minus half a period. And as it turns out, since Z has an epsilon expansion due to it being a series in A and P, we can perform a quick computation right here and get that epsilon as represented by this infinite series, where the series on the right also has an epsilon expansion. And if we just equate like powers of epsilon, we see that the linear term on the right has coefficient 1 and all of the other coefficients have zeros. This will turn out to be a useful, critical, actually, initial condition dictated by the very definition of epsilon, and that's analogous to the infinite depth problem, and the only difference being the Cauchy's and Sinch's that appear here. And first we derive the partial differential equations governing the Fourier mode amplitudes of our ansatz. And the way to do this is to formally take the three equations, the auxiliary, kinematic, and Bernoulli, non-dimensionalized and in conformal space, and into them we plug our three ansatz Fourier series. And so if we plug into the auxiliary equation, we get this nice infinite series differential equation, or I should say this one is actually algebraic since there is no differentiation going on there. And as we will see, it looks quite similar and very familiar, quite similar to its counterpart in the infinite depth problem. The difference being obviously that we have these Cauchy normalization terms, and this actually won't be much of a problem for implementation for efficiency. That's not where the bottleneck comes from in this case. Now, in terms of the kinematic free surface equation, if we just plug in the ansatz, we get an infinite series equation from p equals 0 to infinity. And as it turns out, unlike the infinite depth problem, it's quite nice to actually separate out the equation we get, not try to compactify it for p equals 0 and p greater than or equal to 1. What we do is we separate out the p equals 0 case and get this nice equation. And the reason we do this is because of an eye towards the future, where this is just can be seen as a first order non-homogeneous linear equation in H prime. This will allow us to compute the Stokes coefficients of the height function by simply integrating along with an appropriate initial condition. And that's something that we didn't have in the infinite depth problem, obviously, because there was no height function. And if we take the kinematic free surface equation, non-dimensionalized and in conformal space, and we look at it, what it gives us for p greater than or equal to 1 upon substitution of the ansatz, we get this. And in the Bernoulli free surface equation, just looking back at the slides, I apologize, I failed to mention this. The Bernoulli equation has right-hand side c of t, which is an arbitrary temporal function, and this can be seen as an integration constant in time, and it's arbitrary, and it's nice to be able to set this to something convenient to actually simplify the problem, and this signifies that only the gradient of the velocity potential actually has physical significance. So yeah, so that's something that we have a degree of freedom in. And in the infinite depth problem, it turns out that what Amick and Toland can be proved to be equivalent or tantamount to setting their C of t constant, which they didn't even mention, to 0. And this is where it comes in, because when we plug into the Bernoulli equation naively, what should be done is to separate this out also into the two cases p equals 0 and p greater than or equal to 1. The only thing is that for the p equals 0 function, it's nice to be able to set the p equals 0 equation, rather, I apologize. It's nice to be able to set this temporal potential function in such a way that it kills the first term equation, the 0th term equation, such that it gives us c sub 0 dot equals 0, and this just allows us to set c0 of t equals to 0. Now, since the c coefficients begin from 0, since they're associated with a cosine series, this series can now be taken to commence from 1 instead of 0. So all of our ansatz for A series begin from p equals 1, which is quite nice. And we have this nice equation right here. Now, here's a key challenge that the key challenge that we encounter in this problem, and which only arises since we need to actually implement this stuff on a parallel computer with limited resources. Now, if we take a look at the previous equations, they do a bit remind us of their infinite depth counterparts. The only main difference is that we have cinches and coches of integer multiples of the height function. Now, since these are basically linear combinations of exponentials of integer multiples of the height function, they also can be expanded as power series in epsilon. And since we need to figure out the equations that, differential equations that govern the Stokes coefficients, we need to be able to find a reasonable way to actually be able to compute the exponentiation of a formal power series, in this case, the exponentiation of integers times h. So a naive way would be to realize that we need to compute high-order derivatives of a composition of two functions where the outer function is an exponential, and the naive way would just be to use the Fodde-Bruno formula, where the problem is that the complexity grows exponentially with the order of the derivative. Now, the thing to realize is that since the outer function is not a general function like in the Fodde-Bruno formula generally, but it's specifically an exponential, this means that we can actually use the Bell polynomials from combinatorics to actually get the epsilon series of an exponential of the height function or integer multiples of it in quadratic time. The complexity grows quadratically only with the order of the derivative, which is quite nice. And it turns out that the Bell polynomials actually appear implicitly in the work of Fodde-Bruno, even though his formula predates them. I think Bell published his groundbreaking paper in the early 30s or 20s, I forget. And we define the complete Bell polynomials where Bn plus 1 is a multivariate polynomial and x1 to xn plus 1 n plus 1 variables recursively via the following, where the base case B0 was just the constant 1. And this formula, besides being simple and elegant, is also easy to implement on a computer and not too expensive. In addition to this, through this formula, we have these formulas for the exponential of a power series. That's the first. And through it, we can get the exponential in terms of epsilon of QH, where Q is just an integer. And what happens is we can now write a simple, elegant formula for the Cauchys and Cinches as epsilon expansions, where we have CQN and SQN, these being the Stokes coefficients of Cauchy QH and Cinch QH. And those are the ones that we need, basically, to be able to compute this stuff. And as it turns out, once we plug in, once we take the equations that we just derived governing the Fourier mode amplitudes of the problem and plug into them the Stokes expansions, what we get is this nice system of linear first order non-homogeneous differential equations, much like the infinite depth counterpart system that Amick and Toland actually began with. And as far as the infinite depth condition, we just set this as a matter of a nice convention that A0 and B0 are 0, since the series with A and B and them begin from 1, since they're sine series, so it's nice to be able to set these guys to 0. And courtesy of the freedom to choose the temporal arbitrary integration constant in Bernoulli, we chose C0 equals 0, so gamma z 0 n is 0 for all n's. This is the initial condition. The number Roman numeral 2 is just the initial condition dictated by the epsilon. And the third one is an initial condition that I'll get to just in a moment. And Roman numerals V to 5 to 7 are quite similar to their counterparts in the infinite depth, only we need to add an equation for mu and dot. This one, so we can dictate the, so we can actually solve for, integrate rather, the Stokes coefficients of the height function. And this is actually dictated from our kinematic free surface equation isolated for b equals 0. Now it turns out that once we integrate this fellow right here, we still have a degree of freedom where the constant of integration needs to be determined. And that's where the initial condition number 3 comes in, Roman numeral 3. This is just an initial condition that stems from us constraining the mean free surface height, which is constant in time, as can readily be shown, in physical space to be 0. So if it starts out being 0, it will always be 0 courtesy of conservation of mass. And this will dictate mu n 0 once we actually integrate this guy for mu n. And it turns out that it's nice to actually, on the previous slide, to actually eliminate the gammas from the equations, at least from the homogeneous or the left-hand sides, if you will, but they will stay in these nonlinear forcing terms T2, T3, and T4. So we combine each consecutive pair of equations from Roman numeral 5 to Roman numeral 7, much like Amick and Toland did, just through simple different linear operations, and we get this nice these nice equations. Now, here is a key difference from the infinite depth problem. Roman numeral V star looks actually identical. It is identical to its counterpart in the infinite depth problem. The key observation here is that equation number Roman numeral 6 star is a second order linear non-homogeneous differential equation that looks remarkably similar to its infinite depth counterpart. The only difference here is that while the coefficient of alpha Pn in the infinite depth problem was P, the coefficient right here stemming from the fact that we have finite depth is P coth mu 0 tang P mu 0. And what this implies, basically, the key implication of this is that it cannot be a perfect square here for P greater than or equal to 1, because for P equals 1, it's obviously 1. But for P greater than or equal to 1, it cannot be a perfect square integer under a very mild assumption on the dimensionless fluid depth mu 0. And it turns out that this having the potential to be a perfect square in the infinite depth problem was what caused Amick and Toland's groundbreaking algorithm to be so complicated, because they could have resonance as 0 divisors. And they had to work around them with fancy compatibility conditions. This is something that we won't have here if we just make a mild assumption on mu 0, as I'll get to in a moment. This is the definition of the forcing terms, or these are the definitions of the forcing terms, where this is T10n, and this is T2n, T2pn. And a key difference one realizes that while T2 is basically basically just involves double sum, much like its counterpart in the infinite depth problem. T1, 0, n actually involves triple and quadruple sums, and this hints to the fact that we have this time complexity bottleneck right here, stemming from the fact that we have these cinches and coches of the height function that increase the order of the sums, and thus the computational time that's dominated by the computation of these forces. And this is 3, where it's just as also involves triple and quadruple sums, and this is T4, where it just involves triple and double sums. So the time complexity grows like the order of computing a quadruple sum. And the solution we seek solutions to our differential, the system of ODEs with the initial conditions in the space of trigonometric polynomials of a specific form, where the mu and the Stokes coefficients of the height function, along with the Stokes coefficients of A, are even cosine trigonometric polynomials of a certain form where their max degree at n for mu n is 2n at most, and at Pn for alpha Pn is p plus 2n at most, where the coefficients are real. And this guy right here, in P and beta Pn and gamma Pn, we want them to be odd or sine trigonometric polynomials of degree at most p plus 2n. And we assume that the sigma n are real constants, much like Amick and Toland did, since they're the Stokes coefficients of the expansion of the Freud number, and h of j is just this nice sort of auxiliary indicator function to account for lack of symmetry for the j equals 0 terms. So we need to take half, since 0 doesn't have a counterpart in the exponential. And here's a nice comment. In Amick and Toland's equations, they actually eliminated gamma from the right-hand side and the left-hand side, the non-homogeneous forcing terms, because their forcing terms didn't actually depend on gamma the way ours do, courtesy of the height function. In our case, we could have eliminated gamma completely, because we just eliminated it from the left-hand sides of the equations, but we also could have eliminated it from the right-hand sides of the equations by simply dividing by sinh of pH or cosh of pH, where that's perfectly valid in the case of sinh pH, since in the small amplitude regime we're working on, h can assume to be non-zero, and we can figure out Stokes expansions of the inverse of cinches and coches, which will also be a cosine trig polynomial, but it just adds an unnecessary layer to the sum. So we go to the highest sum being a quintuple sum, which would drastically increase the already enormous computational complexity of this. And just interesting theoretically, just to realize that we can get like full-on consistency even more with their theory. And the second initial condition, as I stated, stems from us constraining a zero mean-free surface height in physical space. And the key difference that I was alluding to earlier and I was discussing is that the term now, instead of P in the second order linear non-homogeneous equation, the last one, in our case, it's P coth mu 0 tanh P mu 0, and it cannot be a perfect square or even an algebraic number for P greater than 1 if we just assume that mu 0 is algebraic, and I'll get to that in a moment. This is actually a quick application of a classic result in transcendental number theory that states that exponentials of different algebraic exponents are linearly independent over the algebraic numbers. And this results in a straightforward algorithm where we don't need to work around non-trivial resonances that occurred in the infinite depth setting for P greater than or equal to 1 when P was a perfect square. And the only possible resonance that we need to work around to avoid is when P equals 1, which was also a resonant point, obviously, in Amick and Toland's infinite depth algorithm. And it turns out that this is necessary to be able to set the sigma coefficients using an orthogonality condition akin to the infinite depth problem to avoid resonance actually and secular terms showing up in the second order equation, whose solution is just a cosine polynomial, turns out. So we just basically want the cos component to be orthogonal to the nonlinear inhomogeneous forcing term appearing in that equation. So if they're orthogonal, no secular term can actually appear and cause the solution to blow up. And this just uniquely dictates sigma n's that we will see in a moment. And the proof of this, actually, I couldn't resist putting it here because it's not usual. It's unusual to apply this sort of theorem in this type of computational problem, and it actually fit on one slide. So if we just assume that p greater than 1 is a natural number and mu0 is a positive algebraic number, such that n being this nice coefficient right here is algebraic to get a contradiction, we may then expand this as the epsilon definitions of these hyperbolic trig functions, and upon rearranging, we get a linear combination of different exponentials of algebraic numbers that they are different because the p is greater than 1 and natural, and mu0 is positive. So all four of these exponents are distinct, and consequently, their linear combination over these algebraic numbers can only be 0 if every coefficient is 0. And this turns out to mean that p equals n equals minus n, which is a contradiction to p greater than or equal to 1. So that's a very nice, elegant proof that we have no non-trivial resonances beyond p equals 1. And this is an illustration of our algorithm, since we now have the system and we've shown lack of resonance for a very mild condition. This is the idea of our algorithm, which is very much in the spirit of the algorithm of Amick and Toland, only in our case, we don't need to work around resonances. So the idea of the algorithm is that each iteration of our algorithm, we know the Stokes coefficients attached to lattice points marked by these pluses on or below the solid line, and we want to expand by the set, or extend it in the set theoretic sense, by computing the Stokes coefficients that are associated with the open markers and the filled marker right here on top that are on or below the dashed line. And it turns out that this is what we do at every iteration, only now at each iteration, we also need to worry about computing the next Stokes coefficient of the height function from mu_n to mu_n plus 1. And much like in Amick and Toland's case, we also need to compute sigma_n plus 1 using the orthogonality condition that we have, or the non-resonance condition on the previous slide, if you will. And if we just define these sets L of nu as all of these lattice points that are trapped below level nu, where for a point Pn, its level is defined as p plus 2n. So basically where they happen to be on one of these lines parallel to the solid and dashed lines. So we basically augment from 2n plus 1 to level 2n plus 3 at each iteration inductively, starting from n equals 0, or level 1, if you will. And gamma nu is just the set of Stokes triplets alpha, beta, and gamma attached to lattice points Pn and L nu. And sigma n is defined just like the counterpart in Amick and Toland, sigma 0 to sigma n. And as it turns out, the set M of n, which we now introduce, is just the set of height function Stokes coefficients mu1 to mu_n. And finding our solution to our problems involves determining the sets gamma nu, m, n, and sigma n, with n and nu being related by this nice quick equation. And the idea of the algorithm, as we stated, is to augment or extend in the set theoretic sense at each iteration gamma 2n plus 1 to gamma 2n plus 2 and 2n plus 3, and to extend mn and sigma n to mn plus 1 and sigma n plus 1, respectively. And we define the set illustrated below as omega Pn, much like Amick and Toland did, only in our case, we don't need to worry about a P0. So it looks like the set of lattice points that are in the shaded region for a point Pn. And the reason we do this is because just looking at the forces, it turns out that the forces T1 to T4 are functions of alpha, beta, and gamma. For JK being an omega Pn for the set at lattice point Pn. Basically, this set just dictates the set of lattice points upon which the forces at Pn are dependent. And also, as it turns out, that T1, 0, n depends on height functions up to n minus 1, which will allow us to compute mn when we deal with point small n, and T3 and T4 Pn depend on the height functions up to n, which makes sense, and we will see in a moment. And T4 Pn depends on sigma n, basically all sigma Freud coefficients, Stokes coefficients up to n, including small sigma n. And the idea of the algorithm is we know the pluses, and we want to compute the open and closed markers. And what we do is we start by augmenting level 2n plus 1 to level 2n plus 2 by computing the points that are on the line parallel to between the solid and dashed lines, which the line connecting them isn't plotted. So we start computing them from left to right, bottom to top, since the order of the forces and the dependence dictates that this is possible. So that's just what we do first. And then what we can do then is just before reaching the, we can keep doing this for level gamma 2n plus 3, only just before getting to the point that's marked by the solid bullet, 1n plus 1, we need to compute the height function mu n plus 1 by integrating the equation for the first order linear non-homogeneous differential equation for mu n. We integrate it, and the integration constant is just determined by the mean free surface height being 0 in physical space and the initial condition it gives us. We then are able to compute everything on level 2n plus 3. And right here is where we, on the bullet, we compute the sigma n plus 1 using the orthogonality condition. And then last, what happens is we can actually compute alpha 1 n plus 1 at that point up to an arbitrary real multiple of cos of t, which is degree of freedom at that point due to us avoiding resonance. And this actually coefficient of cos of t is dictated by our initial condition stemming from the definition of epsilon, much like Amick and Toland did. So that last step is analogous. And finally, we compute beta 1 n plus 1 and gamma n plus 1 by solving or integrating their differential equations. And inductively, if we just follow this argument of the algorithm, this exposition of the algorithm inductively, it turns out that this shows existence and uniqueness of the solution in the space of trig polynomials of the form we want. Just looking at the forces, we see that we either have products of sins and coses in each force or cos and sins. So each force is actually just a trig polynomial that's even or odd. So integration or solving equations won't actually change the form. And a comment I should make is that the Bell polynomials we need for each level are computed as we go along and as we need them. And we also don't need to store the coefficients of the sinches and coshes of H, since those are just sums or differences of Bell polynomials divided by 2. And the basis of the induction argument simply involves computing. Since we know everything at 0, we don't even need to worry about it. It just involves computing alpha 1, 0, beta 1, 0, gamma 1, 0, and sigma 0, which is needed to commence the algorithm anyway, since the algorithm commences from level nu equals 1 and goes on to the next levels. And sigma 0 in this case, unlike the infinite depth problem, is not 1, but coth of mu 0, which is responsible for the transcendental miracle that we had a few slides back. And the induction argument of the algorithm also shows that, much like in the infinite depth problem of Amick and Toland, that alpha pnj, beta pnj, and gamma pnj are zeros for j's and p's with opposite parities. So we only need to store half as many Fourier coefficients when storing these guys as chunks. And it turns out that for mu nj and B, Q, and J, these are zeros for odd J's, since these can be associated with P equals 0. They're the analogy to the height function, to the A0 term, which is not 0 at Amick and Toland's infinite depth problem. And the last observation about the Stokes coefficients of a specific parity being 0 can reduce memory costs, since we don't even need to allocate space for real numbers that we know a priori to be 0. And this saves us a lot of memory, especially since we're working with multiple precision arithmetic, as we will soon see. And as far as the computational aspects of actually implementing this, the trig polynomial structure of our problem makes solving our linear ODEs in Fourier space all the more simple and natural using an FFT approach, since solving differential for equations, linear differential equations in Fourier space just involves reading and writing Fourier coefficients from memory. And we use arbitrary or multiple precision arithmetic and a custom FFT library that's compatible with this on a supercomputer, specifically the UC Berkeley Savio cluster. And it turns out that the time complexity is dominated by the computation of our nonlinear forces, obviously, since in this case we have triple and quadruple sums, unlike Amick and Toland, where they only had double sums. So the order we reach is naturally restricted by this with given resources. And we implement a hybrid OpenMP, MPI, C++ approach, where each thread node pair actually computes a summand And all the summands are using the T1 to T4 are combined or summed using the appropriate reduction at the appropriate parallel level. So in other words, we do compute in the algorithm each level sequentially, but we parallelize the work at the force level since this leads to almost perfect load balancing and keeps most workers busy in the parallel environment. And the thing is that we have sums of products in our nonlinear forces T1 to T4. And as it turns out, we need to multiply Fourier series since each of them is a finite degree trig polynomial. And the way to do this is we just use the C2R and R2C since we know that everything is real valued instead of using the more expensive complex Fourier transform. So we would just need to do a complex to real on the trig polynomials whose coefficients we store, then transfer them to a time-sampled functions on a grid large enough to avoid aliasing errors, and which can grow as the algorithm grows. And then we multiply the time-sampled versions of this, sum them up, and then move back to Fourier space to get the coefficients of the trig coefficients of the sum using real 2 complex, the inverse operation. And as far as the numerical results, a good first question question, an important one that needs to be asked in this type of problem is about the growth rate of the terms appearing in our semi-analytic asymptotic expansions and whether or not they can converge or not. The infinite depth problem was an open question, still remains an open question left unresolved by Amick and Toland's groundbreaking paper. And here what we do is we wish to sort of investigate this empirically, which was a main point in this entire project. So a good first step towards answering the question, how do the terms actually grow and whether or not there is any hope of these things actually converging, or at least showing an empirically convincing evidence that these things can converge or not, is to actually quantify the growth rate. So to that effect, at each level nu, what we do is we define this fellow right here. And the way the reason for this definition is if we look at our ansatz for big Z, it's an infinite asymptotic series in APs and functions of the height function, trig functions, I should say, where AP and HP ultimately, AP and H, the height function, ultimately have epsilon expansions. Ergo, big Z itself has an epsilon expansion, which can be consolidated in powers of epsilon, where epsilon to the nu corresponds to level nu. And the proper way to do this is to look at this eta tilde guy over alpha and t, where we non-dimensionalized the vertical displacement of the standing wave and also rescale time so that in eta tilde alpha t, the alpha and t vary over the standard torus T2. And these coefficients, whose L2 norm discretely we measure here or right here. And the idea is also that since we've done this rescaling of time and working with a torus, this has this nice sort of observation that A nu can now be observed as the L2 norm of this eta tilde nu function on the torus T2, which is also quite nice and standard in this type of work by Professor Wolkening. And here are the first batch of our numerical results, where we plot in panels A and B the growth rate for 6-dimensionless fluid depths. I believe we have 1, 4, 1/4, 8, 1/16, and 16. And we also contrast this with the infinite depth problem's growth rate for comparison, which you've also implemented, but that's in a separate project. And as it turns out, just looking at it, we see that we were able to actually compute the infinite depth problem up to order 109 due to the dominance of and the computational bottleneck of the triple and quadruple sums. As it turns out, we see that we have geometric growth for the different depths, but as we can see, the growth rate is drastically different depending on the depth. For the infinite depth problem, since we only have double sums, we really took it to a much higher order beyond 500, and we actually managed to get higher in the next project with Professor Wolkening. And as it turns out, the cases mu0 equals 1 and mu0 equals 1/4, if we look at the panel on the top right, panel B, these exhibit resonant jumps or kinks in the growth rate at a specific order, which was quite interesting and we'll get to in a moment. Now, as far as measuring the radius of convergence or determining empirically whether these things have any hope of converging, we take a look at not the ratio in panel C, but the geometric mean of two consecutive ratio, a nu over a nu minus 1 times a nu minus 1 over a nu minus 2. And the inverse to this, if we take the lim sup, is actually the radius of convergence. And this is just basic calculus or analysis. And the idea is the reason we actually do we use the geometric mean instead of just plotting a single ratio is to eliminate even odd oscillations that can appear if we just plot the ratio, this sort of on again, off again when we change the parity of the order. So we eliminate that by plotting the geometric average. And as we can see in panel C, these things sort of plateau to a fixed quantity at a certain height. And this plateau makes it reasonable to assume that if we just look at this plateau as rho nu, I should say, at the order from which starts, that makes sense to check it as an effective, or to sort of look at it as an effective radius of convergence within the empirical framework. And if we take a look at the panel on the right where we plot the log of base 10 of a nu times rho nu, where the rho is just this plateau thingy right here, and we for two different depths, mu equals 1/4 and mu equals 1, for the two depths that exhibit the kinks in the growth rate, we see that where we rescale the vertical axis differently for each of the two depths, we realize at the end, asymptotically, or at least to the order we were able to compute, that the sort of fizzle out at a stable level, and we can see the even odd oscillations that would have appeared had we plotted just the ratio in panel C. And as we can see, a quick observation is that mu equals 16 has the highest growth rate of anything here, and we'll get to that in a moment. Now, as far as the infinite depth problem, this coefficient that we had in the equation, p tanh p mu 0 times 1 over tanh mu 0, or coth mu 0, cannot be a perfect square for p greater than 1 if mu 0 is just assumed to be an algebraic depth, courtesy of Lindemann-Weierstrass. However, and similarly to the, but very differently from the infinite depth problem, it can be close to a perfect square, which would introduce near resonances or blowups, if you will. And we don't have actually zero divisors, but we do have small divisors, which is what happens for each p if we just minimize this fellow right here over g's, with g's having the same parity as p, lambda pj, and we plot these for each of our distinct depths. And what we realize is for the four depths that exhibit the kinks, for mu 0 equals 1/4, we see a very sharp spike at p equals 48, which would exhibit the blow up or the resonant kink in the growth rate. And for mu 0 equals 1, we have these spikes at 12 and 19 that would explain the growth rate, but they're slightly less pronounced than the mu 0 equals 1/4 case, which would explain why that case's kinks are less pronounced. And also, in addition to this, if we look at mu 0 equals 16, we see these very conspicuous, frequent, sharp downward spikes, because in this case, since mu 0 because in the case of mu 0 equals 16, this fellow right here is quite close to p, since the ratio of the tangens is just close to 1. So it's basically approximating almost perfect squares. And this case is what we would call perturbation of zero divisors to small divisors from infinite depth to finite depth. And if we take a look at the numerical continuation results for mu 0 equals 1, where we use these bifurcation plots for the spatial Fourier modes of the initial wave profile at 12 and 19, which is where the spikes in the last slide happened for mu 0 equals 1, we see these sort of imperfect bifurcations that seem to correspond to our spikes in the zero divisor plot. And if we zoom in on the solutions that correspond to the marked points on this diagram, we see what you would call parasitic standing waves on top of standing waves, and they seem to be coming in two phases where the wave numbers can be predicted by our asymptotic expansions on the small divisors, I should say. Now, here is where we compare our solution using the asymptotic expansions for the Fourier coefficients at order 19 at mu 0 = 1 for the initial wave profile to a shooting method that was proposed by Professor Wilkening and one of his former graduate students, Dr. Yu, which basically involves solving the problem as an overdetermined the standing wave problem is an overdetermined least squares problem. As we can see, when we increase the order based on the color of these here plots, we see that the asymptotic solution tries to follow the bifurcation branches and breaks down if we look at the counterpart errors on the right column, whereas the shooting method and the Padé approximation of the shooting method are remarkably accurate and the Padé approximation stays very faithful to the actual solution. And this raises an interesting question of whether we can actually propose an asymptotic expansion of a different form where the Stokes coefficients are structured differently in such a way that they won't break down and approximate the Padé approximations that turn out to be faithful to the shooting method solution, which we take to be the approximate exact solution in this context. And last but not least, in the infinite depth problem, we were able to actually get to, I think, order 641 and empirically demonstrate that it appeared that the radius of convergence in that problem appears to be actually convincingly finite, which is perhaps an unexpected result of Amick and Toland's infinite depth groundbreaking paper, and it's unresolved as far as proving or disproving it analytically. And thank you so much. And I did actually make a couple of seconds worth of video for the parasitic standing waves on top of standing waves. I'll just show it to you. It's literally just a couple of seconds. Just I think I have a couple of seconds left. And if we let me just see this guy right here. If we this is a video courtesy of Professor Wilkening showing parasitic standing waves on top of standing waves. Hopefully this illustrates the point more than my rambling. Thank you so much, and thank you.